Good afternoon. Thanks again for inviting me to this event. I think it's really wonderful. I'm, as I mentioned in the earlier introduction, I'm a psychologist originally, and then I moved on to engineering, and I'm in the Department of Industrial Engineering, and I'm actually a professor of data science there, and it's a very unusual title for me, as you will see in a moment. I'm certainly not a typical data scientist. What am I? I'm doing something that's called cognitive engineering, which is the modeling of systems in which humans and computers, mainly today, intelligent systems, collaborate in performing some task. This is interdisciplinary. I still use some psychology, but I also use experimental economics, and I use computer science, and I use mathematics. The models essentially are mathematical models. Intelligent systems nowadays are essentially AI systems based on decision science, machine learning, autonomous systems in various forms, automation, advanced automation, algorithmic control, and so on. I just use intelligent systems as sort of a general term for anything like this. The models themselves are, again, based on all kinds of disciplines. We have normative models, which are based on decision analysis and operations research and game theory and economic theory. And we have descriptive models, which are based on behavioral research, experimental economics, as I said, behavioral operations research, psychology, human computer interaction, human factors. The goal is to generate predictive models that allow us to say something on what's going to happen with a given system configuration or with a given way the system's operated. And this then is translated, or we hopefully translate this into applications. In recent years, I mean, for a decade or so already, intelligent systems are essentially now data-based, right? This has it hasn't always been like this. AI, if you would have studied a course in AI 30 years ago, you would have probably studied Lisp and production rules and things like this. There was very little data, but now AI is essentially data. And this is made possible because of this explosion of data, the enormous accumulation of data that happens nowadays also through, for instance, the Internet of Things. So now we can support decision-making with this data. And we do this with intelligent systems. We do this at different levels. We do this at the level of the government, where public health-related decisions can be based on data. We do this at businesses, obviously. There's a huge AI-based decision industry. And we even do this at the individual level, where we believe that making data available to individuals may help them make better decisions. Okay? We have dashboards, for instance, around COVID or around other issues that are supposed to help people make decisions or inform people in some form. So AI obviously has been extremely successful, right? Mainly in image processing, natural language processing, and so on. There has been much optimism about AI for decision making. This resembles a little bit what happened in the 1950s with respect to management sciences, right? Herb Simon and so was saying at the time, it then changed the tone, but that pretty soon there won't be a need for human managers because you would have the operations research calculations that would say exactly what people would have to do in an organization to maximize some profits or whatever. There has indeed been successful applications. There have been successful applications of AI for decision support. A very impressive study was done by McKinney and others on breast cancer screening, the analysis of images and identification of possible breast cancer, and then decisions to do biopsies. Was published in Science in 2020. And these mechanisms, AI-based mechanisms, work better than radiologists. So essentially, you should replace radiologists by AI here. So this is sort of the typical decision problem I'm dealing with, right? I have a decision problem. I have an algorithm. I can recommend, decide what needs to be done. And now the question is, how do I use this algorithm? Mainly, I'm interested in the question, what is the role humans have if I have such an algorithm? And what I'm going to say is, I'm going to say two things, and I hope I will confuse you. One is that there is absolutely no role for humans, and then I'm going to say that actually there's a very important role for humans. But a few premises first. Systems will improve, right? Even if we don't have very good AI at the moment for decision support, in many domains, we will probably have better systems in the coming years. So, given this, how should one integrate decision support in these decision processes? And specifically, we have to decide what roles people should have in these decisions. Now, I'll use this opportunity to show you a little bit of my own work over the years that has to do with these issues, and tries to answer what exactly the role could be of humans in such a process. Now, the first notion that one often hears when one says, well, I have AI, I have a person, and how can I sort of make them work together is we can create some synergy. We can have AI support the human decision making. Okay? Decision support can help to make better decisions. Now, we have done some empirical work, and this is just one study. We did quite a few other studies in which we had people make decisions. This is a simulated image analysis task where they had to identify whether a certain number appears in this image. And we had this with better and worse decision support. And the dashed lines are what they could have achieved if they would have used the decision support, only relied on the decision support, nothing else. So here, this point should have actually been here if they would have simply ignored any information and simply responded to the decision support, this red or green area here. And people did not use the decision support optimally. Actually, in this case, if instead of running this experiment, if this would have been an actual system, if I'm sort of running this with the person, if I would have automated the process and simply used the decision support as the decision, performance would have been better. Just to say something, the D prime here is a measure of the performance. It's taken from something called signal detection theory. It's similar to the signal-to-noise ratio in electrical engineering. It's equivalent or very immediately transferable to the area under the curve if someone knows from ROC curves, right? It says something on how well a decision maker distinguishes between two different types, or similar to F1 if you know these things. A higher E prime obviously means that people are better able to distinguish between things. But it's not only that people are sort of not functioning well. It turns out that it's actually extremely difficult to improve decision making if you have two decision makers. In this case, I consider the algorithm as a decision maker and the person as a decision maker. If you have two and one of them is better than the other, the added value of the second decision maker is relatively small, right? This is the ratio between the effective D prime, the D prime of the combined decision making, and the human D prime as a function of the weight that is given to the information from the algorithm. And what you see is, essentially, I won't go into the details, but what you see is if you have a better human, D prime automation to D prime human, if you have a better automation, let's say 3 times automation, 3 times better than the human, then the moment you give the automation a sufficiently high rate, the system performs actually very, very, very well. If you don't give the automation the right weight, then performance becomes much worse than having the automation alone. Okay, so basically the idea is, in order for me to get the benefits of two decision makers, I have to assign correct weights. Otherwise, if I don't do this, and it's highly unlikely that people will do this correctly, I'm better off using the better of the two decision makers alone. The second notion is, well, people can't really make joint decisions with the algorithm. then let's maybe have the algorithm, if it's a good algorithm, make the decisions alone, but people will tweak the settings of the algorithm, right? The parameters the algorithm has, right? And in many systems, we actually have people adjust system parameters. Here again, we did some studies. We won't go into the details. We don't have time. If you're interested, I'll be happy to share the papers. But essentially, it turns out that people are very bad in identifying the correct setting of a system parameter. And furthermore, here too, mathematically, it's often impossible for them to be able to set the correct system parameters. And the reason is simply that the number of observations of the system that is required in order for them to determine what the correct system parameter is so large that in a practical context, they will never get a sufficient number of observations. So we cannot expect them to know when they should adjust a system parameter, right? So this notion also doesn't work. A third notion, should actually be three, is we should keep people involved in the process, right? We often hear this, right? Well, they can't make good joint decisions, they can't really adjust the parameters, but it's really important to have people involved in the process. We have this, for instance, with autonomous weapon systems, where practically everybody requires what's called meaningful human involvement, right? You want to have a human involved in the process. Or we have this in GDPR, right? The General Data Protection Regulation in Article 22 requires that people are not subject to algorithmic decision-making in decisions that affect their lives. So a bank is not allowed to decide whether someone gets a loan based only on an algorithm. Okay? A human needs to be involved in the process. What exactly does this mean? It's not quite clear. So we modeled this, actually. We have a model with Nirdur, who just finished his PhD with me, where we try to compute the human involvement in such a process. We looked at it again, sort of more engineering terms. Here we use information theory. We look at it in terms of entropy reduction. We say there's uncertainty what the action is going to be, and there is eventually a certain specific action, and we can look at the reduction of the entropy of the uncertainty over the course of the process, and we can compute the proportion of the entropy reduction that is due to the human. And this is the human involvement. And it turns out that if I have good automation, where the ratio between the d prime of the automation and the d prime of the human is, let's say, 2 or higher, so the automation does the task at least twice as good as the human, human responsibility is 20% or less. Okay? Now, it doesn't make sense to have bad automation. So nobody wants to install a system that is bad. So we will usually have automation that is somewhere above 0.2 or higher. So again, in most cases, if I have a good system, human responsibility, human involvement will be relatively minor, even if I demand it by law or some way, or some form, right? So we're in trouble. And a possible misanthropic conclusion of this would be that humans won't really have a role in decision-making when systems will be intelligent, when we have really good systems, right? So we can all at least forget about the decision-making part. But actually, that's not so bad, right? It's not something that is necessarily negative. Meal in 1954 already published a famous paper on statistical versus clinical predictions, where he showed that statistical predictions are systematically, consistently better than clinical predictions. So the idea of having a human involved in making a clinical decision is actually not a good idea. This finding has been replicated many times. Recently, for instance, Kleinberg and others did a study on bail decisions by judges, and they showed that algorithmic bail decisions are better than the decisions made by human judges. Also, if we have a good algorithm, there may be something like that's called Dietforst and others call algorithm inversion. People may not be willing to use a good algorithm. So if they are not willing voluntarily to use a good algorithm, and they're willing to accept bad decisions because of this, then maybe we should just simply eliminate them from the process and rely on the algorithm, let the thing run automatically. No? So we could think of eliminating people from a decision process as something that is potentially beneficial. Okay? So this is the first idea. People are really unnecessary in decision making. And here I move to the second part, where I'm contradicting myself. People, and in particular social scientists, may actually have a very important role, I would argue. Now let's first look at what exactly does it mean to make database decisions. There is a naive view of database decision making, which assumes, and these are very reasonable assumptions, that the quality of information determines the quality of decisions. Better information means that you make better decisions. And obviously in medicine, someone already mentioned this, evidence-based medicine is something that has been asked for a long time, a few decades already, because it's better than intuition-based or tradition-based medicine or whatever. So now the idea is that we have a question we want to answer. We get data that is relevant for this question. We analyze the data. We present the results. And we answer the question. And it's a wonderful process that will lead us to the best possible decisions we could reach. And this may actually use a lot of ambiguities, things in which people don't agree with decisions, and so on. Right, in social sciences, this was pushed, with respect to science, and not only social science actually, this was pushed to an extreme in an approach that was, for instance, shown by Anderson in a piece in Wired in 2008, where he claimed that pretty soon there won't be any scientific theories anymore. We don't need theorists. You can simply have all the data, analyze it, and all the answers are just there, right? Scientific method will be unnecessary. All we need is data. But as this slide indicates, I believe that this is a somewhat naive view. The view describes the data analysis as a mechanistic process. But what I would like to argue is actually that data sciences and the use of data for decision making is a human activity that concerns human activities. And we cannot do this correctly without considering this being a human activity very closely and understanding, without trying to understand the human activity of doing data science and the human activities that generate the data, these two parts. So we have data human activities involved in the data generation, in the analysis process, in the interpretation of results, and obviously in the implementation of the conclusions from the process. Once I have an algorithm that provides me with some results, I want to do something with this, and again, this is a human decision. Let's have a sort of zoom-in look at the analytics process. Look at it more closely. What is a data scientist actually doing, right? If my students, many of them are becoming data scientists, and they believe what they are doing is they get this important questions, they get the data, they sit down, they run the algorithm, and they give answers. What are they actually doing most of the time? What are data scientists or people who are working on data scientists actually doing? Most of the time, they're actually doing pre-processing. They're cleaning the data, right? So that's the main task for data scientists, right? We have the world that generates some records in some form, somewhere, and so on. These records are somehow combined, okay, in some data warehouse or and so on. From this data warehouse, we select relevant data that we believe can help us make informed decisions here. Then, after we have this data selection, we do data processing, right? Pre-processing. We get rid of duplicate data. We get rid of outliers. We deal with missing data, and so on. And then after we do the data processing, we have the data for the analysis, hopefully in a form that is relatively easy to analyze. And then we prepare this for analysis, maybe recode some of the data and so on, rerun the algorithm. And again, this is not something that is simple. We have to decide on which algorithm we are going to use. We have to decide on the meta parameters for running the algorithm and so on. And then after we run the algorithm, we get the output. And again, we have to decide on what output we want. Visualizations, which visualizations, how exactly is it visualized? And then we interpret the results. And we make with these results whatever we want to do. Each of these arrows is actually a set of decisions that are made by humans, right? Each of them are decisions people make. And each decision affects what's happening in the next step, right? So there is very strong human involvement in this process. And we have to consider this. Each decision depends on the beliefs, preferences, costs, benefits of the people who are involved in this process. And of course, it affects the course of the analytics process and its outcomes. So this is the analytics process, but I'd rather now even like to look at the things that comes before the analytics, the raw material on which analytics is run, the data part, okay, the input for the analytics process. Analytics are based on data, and we believe that the data reflects reality. Okay? So we want to have some image of the real world in some form that allows us to make decisions regarding this. So here we could look at this as three different realms: the physical world in which things happen, the social context, and the individual that interacts with the physical world and the social context. And we have the digital representation. And the digital representation is actually the traces from the physical world, and the traces from social interactions, and the traces of the individual's actions that are somehow recorded, and they are the basis for our analysis. Okay, they are the input for any data science we do. Now, if we have a one-to-one representation between the physical world and the social context and the individual action, the digital representation, then everything is wonderful. But we never have an absolute, full, complete, and correct representation. So the digital representation is always somewhat different. We may have incorrect representations of the physical or social realms, or incomplete ones, and physical properties of the world may affect the way the representations are generated. Let me show a few examples. I think some of them are familiar, maybe more familiar. We usually analyze data we have, right? We have in our database. But I like this term. I'm trying to write a paper about this, the big data of non-existing data, right? Because we know that there are things that are not in the database, that are by definition almost not in the database. And we need to consider this. The example here, Abraham Wald is a well-known statistician. He worked with the US government in World War II. Among other things, he tried to help them decide where to put armament, sort of reinforce airplanes to minimize the chances of being shot down. And so the way he approached this is by analyzing the planes that came back from missions and looking at the anti-aircraft gun holes in the airplane. And he recommended reinforcing which parts? Not the parts where you had most bullet holes, but rather the parts where there were no bullet holes. What's the reason? Planes that came back with bullet holes came back. Planes that got shot down did not come back. And the thing that probably distinguished between these two types of planes was that those who did not come back got shot in the areas where you don't have bullet holes. Because if they would have gotten shot there, they would have gone down, right? So we know that there are planes that were shot down, and they probably were hit in these areas. So they would not appear in a database. Similar story is told about the use of steel helmets in World War I. The claim was that the British higher command actually was very unhappy with steel helmets because it greatly increased the number of people who were in field hospitals with head injuries. Now, indeed, the number of people with head injuries increased with steel helmets. The reason was that without the steel helmets, these people would have been dead, right? They would have not have come to the hospital. So again, we have non-existing cases that we need to take into account. Or here, Hurricane Sandy, data from Hurricane Sandy, an analysis of Twitter activity as an indication of the amount of sort of concern with the hurricane and so on. Sandy was the most severe hurricane that hit the upper east coast of the US ever since there are recordings of hurricane strength. 53 people dead in New York State. If you look at it, the most Twitter activities in Manhattan and in Brooklyn. Actually, Sandy hit the New Jersey coast and Staten Island and Long Island worse because they're obviously right on the Atlantic. Why was there no Twitter activity? Well, two reasons. One is that people left, so they couldn't tweet. And the second was that the hurricane was pretty bad, so cell towers were toppled. And if you don't have cell communications, you can't tweet either. So you cannot really decide on the strength of such an event from Twitter activity without taking into account how exactly Twitter activity is generated. Or here's some work we did a few years ago when I was at MIT, the group at the Human Dynamics Lab, at the Media Lab. We looked at credit card transactions during social unrest, and we had credit card data for a Mediterranean country. And again, we looked at the credit card data. We got some responses. It's a little bit geographic. I'm trying to show the most geographic studies I have here as a function of the distance from the epicenter of the social unrest, and the effects were strongest closer to the epicenter. But we only have credit card data, and we know that there are cash transactions. So what exactly happens there? We try to do something on measuring social distances through cell phone metadata. And again, we have an interesting issue here because if I am closer to someone, I'm actually communicating with the person more. Okay, that makes sense. But I don't communicate very often with my spouse when we are living together, even though she's probably the closest person to me, right? Because we are living in the same apartment. So I don't use WhatsApp very often. So that we have a non-linear relationship. And finally, let me show a study that is a little bit more geographic than most of the stuff I do. We did some research on the crime in the UK, in London, trying to understand the frequency of crime data, of different crime events in different geographic areas. This is Omer Miran's MSc thesis. We looked at two types of crimes, burglaries and drug-related crimes, where the difference is that burglaries are actually reported by people who are the victim of burglaries. Drug-related crimes actually are not reported unless there's police. So data on burglaries reflects crimes. Data on drug-related crimes reflects what the police does. So we combined 4 data sets. The UK police is very good at this. It really provides open data on crimes, and it provides open data on stop and search. So we actually know how many people are stopped in the street by the UK police, and it's all open. And we looked at population and average income data set, and data sets and so on. Normalized it, we won't go into the technicalities. Got rid of outliers. What's the point up there? This is the amount of drug-related activity per population, 10,000. This is the amount of burglaries. We have one data point up there, which is the point with the highest per population drug-related and burglaries. It's the city of London, because it has a very small population, and there are hundreds of thousands of people actually moving through there every day, so you get a very high number of events. So we developed some model. The important point is that there was no correlation between police activity and the level of crime. as measured through burglaries. Okay, so that was to be expected. But there was actually a positive correlation between the number of stop and search actions and the number of recorded drug-related crimes, as we predicted. This reflects police activity. The UK and Wales has a drug survey, and in this drug survey, 2.8% of the adults reported using drugs at least once a month. This means that about 280 people out of 10,000 should use drug at least once a month, which means that there should be about 3,360 drug-related crimes per year per 10,000 people. In our analysis of the UK data, we find that approximately 28.7 cases of drug-related crimes in this database, which means that there is approximately 1 to 100 ratio between the number of cases that appear in the database and the number of cases that apparently should have occurred or should occur according to what people say about their own drug use. So some conclusions. I'm really, really strongly convinced that data is essentially the basis for decision making. We have to use data for decision making. But the analysis process, the analytic process, is a human activity that one has to understand. And very much of our decision making, especially as social scientists or people who are dealing with things that happen in social organizations and so on, is concerned with human activities. And we cannot do this kind of work without applying more traditional social sciences approaches to understand human behavior. We have to observe actually what people are doing, and we have to use these observations to understand the analytics process. So what is the basic conclusions? For data scientists to provide useful support for decision making, the algorithm analytics process must be accompanied by models of the behaviors that generate the data. Traditional modeling techniques, not just data science modeling, sort of features and so output, but rather traditional modeling techniques and data science methods should be combined. And this is important for improving decision making and utilization of data. And to do so, I think one of the important things is that we need to train data scientists in social sciences, in classical social sciences. They need to be able to go beyond the algorithm and understand what the behavior is that they are actually trying to model. And obviously, interdisciplinary teams can be very useful here. Thank you very much.